In this section, we're going to go over some best practices for pre-processing natural language data so that our vector spaces that we create, as well as our downstream natural language applications, work as efficiently as they can. So I already have created for you a notebook, Natural Language Preprocessing Best Practices, so you can follow along in there. Or you can work alongside me to create this afresh, so we can see things step by step. So we're going to call this notebook Natural Language Preprocessing Best Practices. And this is a demo notebook. And give it some kind of title here. Best Practices for NLP. And some kind of note about what we're doing in here. We're creating word vectors after pre-processing our natural language data. And we are going to load some dependencies, as we always do. The first ones that we load are going to be the same as in the previous lesson. So I'm just going to head back there into that notebook and copy and paste that first block of dependencies. And likewise, we are going to need to download the Punkt dataset. And we also have some new imports. So we're going to import string. We're going to have some additional NLTK functions. So from corpus, we're going to import stop words. I'll explain what those are in a moment. Likewise, we're going to need some stemming tools, which I will also explain in a moment. And we're going to need tools for creating bigrams, which I will also explain momentarily. Finally, I'm going to show you a really helpful keras function for importing and encoding word vectors in a single shot. So that's the one-hot function. Another dependency we're going to need is this dictionary of stop words. So let's pull that in. And let's load in our data. Now this may already be downloaded for you. If you did this earlier. If so, it will be a very quick download because it will know that the files are already there in place. And we're also going to need to import our Gutenberg documents, which are the 18 texts that we were working with earlier. And we're going to skip right through to tokenizing them into sentences. And within those sentences will be tokenized words using the very convenient sense method on the Gutenberg object. Great, so that was easy. It's the same as we did yesterday. And then we're going to pre-process a sentence here. I'm going to show you a number of natural language best practices. So we're going to pre-process an individual sentence to give you a sense of how that works. So let's have a look at one of the sentences that the sentence method already tokenized for us. So we'll look at the fifth sentence. And so here you can see it's clearly a sentence that's broken into a list of words. So she was the youngest of the two daughters, etc., etc. One of the things that we noticed in our vector space plot yesterday that we made in Bokeh was that words that started with a capital letter and words that were all lowercase were both in our data set. Now, typically, words that are all lowercase or have a capital letter at the beginning are identical in meaning. So we can convert all of the words in our data set to lowercase, and it is quite easy with a single function. So we're going to convert to lowercase our sentence, and to do that, we can put everything into a list comprehension for efficiency to process across all of the words. So for every word in the Gutenberg sentences, sentence 5, we're going to use the lower method to lower all of those words so that the uppercase words like she should be lowercase after we run it through that lower function. Yep, so there you go. So now every word in the sentence is all lowercase letters. In addition to converting all of our words to lowercase, another common practice in pre-processing natural language data is to remove the punctuation, because punctuation tends not to be thought of as a word, of course. Although when we tokenize, as you can see in our sentence here, commas and periods, semicolons, they are all present as tokens, but we don't want to be training our vector space on that punctuation. We also want to remove stop words. I'll show you what those are in 1 second, and it will make sense to you what they are and why we want to remove them. So up above, we imported a stop words object, and we want the English words from it, so we'll specify that. And we're also going to say that our punctuation points are stop words just for convenience later on. And so we'll use the string punctuation call. And so now this stop words object is a list of the stop words, like I, me, myself, all of these words that are quite common in language, so they appear throughout our corpus, but they don't really convey much meaning on their own. Depending on the size of your data set, you may want to leave stop words in. So if you have a very large corpus, then it might do very well with these stop words, or you might want to just remove, a handful of the most common words instead of the specific list of stop words. There are a lot of different ways you can consider pre-processing your natural language data, and the best way to check what the right thing to do is to experiment with a few different ways. At the bottom of this list, we also have the punctuation marks that we want to remove from our sentences as well. So let's create a list comprehension now that does both lowercase, the sentence, as well as remove stop words and punctuation. So we can use the same list comprehension that we had above, so we'll copy it and paste it as a starting point. And then we will add a qualification at the end, which is if the word is not in stop words. So if it isn't in stop words, then we output it. And so now you can see the sentence is quite a bit shorter. So we used to have this relatively long sentence with all these punctuation marks and words like of and and the, which don't convey very much meaning themselves. And now we're down to simply the words that have a lot of a meaning attached to them. Nouns and adjectives, for example. Another best practice when pre-processing natural language data is to stem words. So stemming words simply means truncating them down to their meaningful bits. So let's have a look at that. So we're going to create an instance of a Porter stemmer. Porter stemming is one of the most common algorithms for stemming words. And let's copy and paste our list comprehension again so that we don't have to type it all out. And this time, we're going to convert all of our words to lowercase as before. We're not going to include words that are in our stop words list, so that's our stop words as well as punctuation marks. And in addition, we're now also going to apply our stemmer. So we can use the stem method. Let's try that out. So now you can see words like daughters have been turned into daughter. Consequence has been dropped down to consequa, and I suspect that's because a word like consequential could be elsewhere in the dictionary. House gets truncated down to house, probably because housing is another similar kind of word. Early and earlier are very similar kinds of words. With a large corpus, you may not want to stem your words because things like early and earlier have subtle differences that a large corpus can capture. But with a smaller corpus, you will likely want to be applying stemming. Again, that's another one of your preprocessing options that you'll want to compare using against your downstream task, whatever final natural language processing task you are completing. Another often practiced idea in natural language preprocessing is to handle bigrams. So bigrams are words that occur right next to each other so often that they kind of mean, they kind of should be brought along together. So phrases like thank you or New York City, these are examples of separate words that we might want to treat as a single concept. To do that, we can use these phrases and phraser functions. So it's a two-step process, and I'll explain why in a moment. So first, we will train the detector, which is called phrases. And so into it, we feed our list of sentences. This will take a few moments to train. As a second step, we want to create a more efficient phraser object for transforming sentences by paring away some of the information. So that happens in a second step. So we can create our list of bigrams by applying the phraser function on the phrases object. You could do that in a single step. And so later on, now after I've shown you that, we can just do this in a single step. It's a linear thing using the phrases and then the phraser function. There are no particular parameters that you need to specify. So let's have a look now at the bigrams that have been pulled out. So here are the bigrams that were pulled out using the default parameters. So there are two quantities that are taken into consideration when the phrases detector is detecting bigrams. So the first thing is the count. So how often do the words to and daughters occur next to each other? And the second thing is a score. Now, the score represents in our corpus how often these words occur together as opposed to how often they occur apart. So, for example, long ago, these two words tend to occur together a lot. They don't tend to occur as often on their own. An even stronger example is Miss Taylor. So this is a character from, I think, one of the Jane Austen books. And Miss Taylor, these two words essentially always occur next to each other, so it has a very, very high score. Now, we are seeing all kinds of bigrams in here that we may not want to be considering as bigrams. So her sister is not a meaningful chunk of two words that should always be considered together. So I think we need to raise our thresholds a little bit. Just before we do that, let's have a look at how this works, how this bigram situation works on passages of text. So John lives in New York City. Let's consider that sentence. and then we're going to split it into a list. Now, if we take that same sentence and we run it through our bigram object that we created above, we'll see that New York is now treated as a single token. So you can see the difference here. If we don't use the bigram object, then New and York are considered as separate terms. If we do pass it through the bigram object, then our list has New York as a single token, which makes a lot of sense. Now you can also create trigrams so that you can handle New York City. But I tried that with this data set earlier, and we didn't have enough instances of New York City occurring together in our corpus for it to create that trigram. Okay, so now we've played around with a particular sentence quite a bit, and we've examined how various preprocessing steps can be applied. Now let's discuss applying those preprocessing steps to an entire corpus. So let's work through that. So we're going to preprocess our Gutenberg project corpus. To do that, we are going to start off by creating a list of all lowercase sentences. So we're going to start off with an empty list, and then we're going to iteratively, with a for loop, go through all of the sentences that we have, and we're going to append the lowercase sentences. So to do that, we're going to use a list comprehension, just like we did above. So for every word in our sentence that we're looping over, if the word is not in our list of punctuation marks. In this instance, for reasons we'll see in a moment, I am leaving in the stop words, and that's because I want to train the bigram phase on our stop words as well, because some of those could end up being important pairs. So at this time, all we're doing is excluding words that are punctuation, excluding tokens that are punctuation, and we're converting all of our words to lowercase. That'll take a moment to run over all of our sentences. So now let's have a look at how they look. Let's look at the first 6 of them. We've got to write out the whole object name, of course. So you can see now that instead of having any capital letters on Emma and Woodhouse, these are all lowercase letters, and all of our punctuation marks have been removed. We don't see any punctuation marks as words in our lists. So great. So that first step worked perfectly. Now let's look for bigrams in amongst all of those lowercase words. So now we're going to do our phraser and our phrases in a single step instead of 2 separate steps, and we're going to do it on the lowercase sentences. Now let's have a look at the bigrams that came out of it. So we're seeing some that we saw above, like 2 daughters. We're seeing words like Miss Taylor, Mr. Woodhouse, which are ones that are excellent bigrams, and these have pretty high scores as well. They occur fairly frequently, 132 times for Mr. Woodhouse. So some of these bigrams we certainly want to retain. Some of them are not really bigrams, so I think our thresholds are too low. So 5 years, those 2 concepts, 5 and years, should be treated separately. They shouldn't be treated as a single bigram. So we need to set some new thresholds. As a quick test that everything is worked out, let's use that sentence from earlier. John lives in New York City. But we have to use all lowercase this time because now all of our data are in lowercase. And we're just going to make sure that this is still working properly on that that sentence. Yep, it's working perfectly fine. So now it's converting New York is lowercase into a single token, New York. And let's now rerun, selecting some slightly higher thresholds. So we're going to use phraser and phrases again right after one another. We're going to apply that to the same lowercase sentences object, but this time, just from eyeballing these data, I'm going to say that the minimum count, the number of times that we see that bigram occur in our corpus, we want that to happen at least 32 times. And we want our score threshold to be at least 64. Now let's see how that looks. So this is a much shorter list now. And not all of these are perfect. Of course, the larger the data set, the more you can tune your minimum count and your threshold to get bigrams that you're happier with. But for the most part, this list looks pretty good. So we're seeing a lot of concepts that are spread across two words, like Jesus Christ, treated as a single concept, which seems to make sense. Holy Ghost. These names from our Jane Austen novels are treated together. So that makes a lot of sense to me. It's not perfect, but that will do for now. In the 2011 paper by Moss et al. That we're taking the IMDb movie sentiment data from later on, they chose to leave in stop words because they think that particular stop words are indicative of sentiment. And they also elected not to stem because they said, and an argument can be made, that a Word2Vec model will learn similar representations of words of the stem whenever the data suggests it. So we are also going to leave in stop words, and we are not going to stem, but you are welcome to experiment with that on your own and see if that changes your results. So now we only have one last step to go. So we're going to create a new list of our clean sentences. So for every sentence in our list of lowercase sentences, we're going to append our sentences after they've gone through our lowercase bigram filter. So that'll take a moment to run, and then we can have a look at our clean sentences. So let's look at the first 10 and see if we can see any bigrams. There's one, Mr. Woodhouse, Miss Taylor. So it looks like everything worked appropriately. We can have a closer look at that sentence in particular, which is the 7th sentence. There it is. And now that we have created these clean sentences, we can run them through Word2Vec, which is similar. In fact, I think the code is identical to the one line that we used to run that earlier. So let's grab that line of code from our creating word sentiment notebook and paste it in here. So we're going to create a model using the Word2Vec function. We're not going to pass in the Gutenberg sentences. Now we're going to pass in our clean sentences that we've cleaned up. We can still have 64 dimensions. That seems like a good starting point. We're going to use the skipgrams architecture of Word2Vec, which has a recommended window size of 10. So it'll be considering 20 context words in total, 10 to the right and 10 to the left of our target words. And let's also increase our minimum word count to 10. We were seeing some pretty rare words in our Word2Vec earlier, so I feel comfortable increasing this up to 10 so that every occurrence of that word has a better chance of being put in the right place in the vector space. And you can run and save this model at home. So I saved it as a file called clean Gutenberg model.word2vec. However, I've already done that. In the interest of time, we can simply load those data in. So let's load in with the word2vec loading function. Great. And let's see how many different words we have in our vocabulary now. 10,000. That's down from, I think, 17,000 in the earlier one. And that's a function of us cleaning up a lot of words. So we've removed punctuation, and we've also increased our minimum word count from 5 to 10, which will make a difference in cutting out those rare words. Now let's have an explore with our model. So let's have a look at a word that we couldn't have looked at before because it's a bigram, and that word is ma'am. So previously that would have been split up into ma and am. And now we can see that we have a bigram for that, and it has, of course, 64 floats representing its location in the 64-dimensional space that we specified above. And now we can also do arithmetic on ma'am. So we can use this most similar method that we were looking at earlier. So we're going to do the kind of king minus man plus woman, but we're going to do a bit of an inverse. So we're going to do ma'am minus man, or minus woman plus man. So we'll see how close we can get to what I would assume that sir would be a good equivalent. If we start with the word ma'am, and then we move along the vector space, kind of removing the female gender component and add in a male gender component, the equivalent should probably be sir. And that does not show up for us. So we'd need a larger data set for that to work out. We can also see some tokens show up in here, like these double hyphens that probably should not be in there. And so if we were interested, we could go in and clear those up. We could add that to our list of punctuation terms that we'd like to remove from the data set. For now, we'll just press on. As a bit of a sanity check, that ma'am example didn't work out. But let's make sure that this data set at least looks good for some arithmetic across our vector space that we were doing yesterday. So let's do father minus man plus woman. That should bring us to mother, and it does. Great. So now, like yesterday, we're going to reduce dimensionality with tsni so that we can have a look at our plot. So that code is the same as in the earlier lesson. And so you can copy and paste it from there. I've already done these steps and created the chords underscore df data frame. So we will simply load that in. You just need to follow these steps right here to create the chords df data frame, and then I saved it away with the toCSV method. Just as we did with the raw data, I did it with the clean data that we have now. So let's load that in. Chords df, use pandas read CSV method to read it in. We have the clean Gutenberg tsni file. And just like yesterday, we're going to plot a scatter plot. So we can copy and paste that from the earlier notebook. And you can see it has a different shape, of course. But now we want to really be able to dive in there and have a look at the individual words instead of just looking at the dots. So let's use some bokeh functions. We're going to use their output notebook function. And then we're going to create a subset of all of our data because I found that the bokeh plot was a bit jittery if we use all 10,000 data points. So we'll take half of them, a random sample of 5,000 of them, and then we can use the same plotting functions that we did yesterday. So let's copy and paste them. I'm just going to make the width and the height a little bit smaller for plotting on this particular screen. And then we can use the show p function to actually bring that up. So here we go. Let's explore this space. So we can zoom in with the wheel zoom option. And we can see that all kinds of proper words and places are showing up in roughly the same place. So words like villages and cities, of course, these are fairly similar words in terms of meaning, and they show up together in this vector space. Words like Israel and Jerusalem are close by. Slightly further away is Syria, which makes sense. It's still a place, but is not as closely related as Israel and Jerusalem are to each other. And we have all kinds of words. Longitude and latitude, of course, end up together. So I'm pretty happy with this space. You can explore around and identify all kinds of interesting clusters of words. And great, so this is looking pretty solid. If you were interested in sharing a vector space that you've created with anybody else, you can use the output file function, which is also provided as a part of bokeh. And then that can create an HTML object that you can share. Anybody can open up in their browser and explore the vector spaces that you create. So now, following some natural language pre-processing best practices, we've created a vector space that we're happy with. Now we can use this information to actually complete a downstream natural language task. So we're going to be classifying documents by their sentiment. Let's get to that next.